So this one was causing some difficulty. Let's talk about it. So they're really setting you up here by, they told you this is point A here. This is A, and this is B. Normally they don't give you this picture. I think there's maybe another problem where they don't give you the picture. And there's point P, and they're asking you for the distance from P to the line formed by points A and B. But they did half of the thinking for you because they showed you a vector AP. They gave you a lot of help here, and then a vector. They showed you the vector AP, and they showed you the vector AB. And so now we're trying to figure out what is this distance, right? What is this distance? And so we know that that distance is almost synonymous with the vector, right? That the vector from this mystery point here. So we'll call this point C. So if you had the vector CP, you could easily get the distance, right? It would be the magnitude of that vector, right? So can we get the vector CP? So this is exactly what I was referring to last time. How could we get the vector CP? Or PC, whatever. So yeah, CP. So if we got the vector CP, we'd be home free. It'd be a piece of cake from there, right? So any other vectors along the way that might be helpful in getting vector CP? Yeah, AC, right? So if we got AC, then I'd have this triangle out of AC and AP. And then how could I get CP? Two different, so yeah, so I could either get vector CP easily or the magnitude of CP easily. Two different approaches, but same thing. So if we could get the vector AC, then what we'd have left is we'd have this triangle, we'd have the vector AC, we'd have our unknown vector, and the vector AP. So I think these are, I think I'll just stop there. I think you can figure it out from there. We're just applying. So, first question is, how do we get AC? Well, that's just a straightforward application of a tool that you have. Okay, that's a tool that you have in your toolbox. And then once you have AC and AP, how do you get that vector? Well, that's just a very basic relationship of vectors, right? Because this will be orthogonal, right? So that the relationship of those three vectors is a fundamental relationship in vector operations. Okay, I hope that helps. Okay, so let's, you guys did your cross product investigation. So let's talk about that. Today we're going to talk about cross product. What does it mean, right? So when you get into vector calculus, cross product and dot product show up in the midst of much harder contexts. So what's going to make those contexts more understandable is if we really have a good understanding of dot and cross product in the first place. All right. So what are some basic observations you made? You did the first 7, or you sketched the first 7, and then you were supposed to kind of predict what the ones at the bottom were. So what'd you observe in the first 7? Maybe some easy cases first. What was an easy case? Alyssa.
When the vectors are pointing in opposite directions, or if they're pointing in the same, resulting in 0.
Okay, so when the vectors were in the same direction or in opposite directions, and we can summarize those two cases as what? Parallel, right? Parallel vectors, opposite or same direction. You get the 0 vector, right? Okay, another observation that you made. Yes, sir?
The vector that it makes is always orthogonal to both of them.
Okay, good. Yep. So notice that the resulting vector of the original two, A and B, is orthogonal to A and orthogonal to B. That was a good observation to make, and that's later in the slide. What about some other cases here, special cases here? Did you observe? Yeah, Christian.
It reaches its maximum value when A and B are orthogonal.
So A and B are orthogonal. So are you talking about the magnitude?
Yeah, the magnitude.
And what is that maximum magnitude? Or you probably, I don't know if you can. Yeah, so you might, maybe hard to know for sure from those examples. But if you have orthogonal vectors and you take the cross product, so here we're just talking about the magnitude then, the magnitude of the cross product, right? Because the cross product is a third vector. The magnitude, if they're orthogonal, is the magnitude of the product of the magnitudes when they're orthogonal. What about if they're not? So they're not parallel and not orthogonal. Neither parallel nor orthogonal. What might we conjecture here that the magnitude is? So when they're parallel, or there's 0. When they're orthogonal, they're maximum, the product of the magnitudes. So what in between? What would it be? If we kind of glean what we talked about with dot product, and now we take these two facts, and we think about dot product. You might conjecture that the magnitude of the cross products when you have an acute or an obtuse angle. Anybody? Product of the magnitudes? Less, right? Less. And how, like, it's kind of like the same thing with dot product, but now it's like the magnitude is the product to the extent that they're orthogonal. When they're orthogonal, you get the product of the magnitudes. When they're parallel, you get 0. So in between, what might be a really good guess for what the exact cross product is?
Sign.
Yeah, so like times the sign, right? So in as much as they're orthogonal would be taking the sign, right? The sign would be the amount of the one that's orthogonal to the other. That's what sign is. Now we're just talking magnitude here, right? We're just talking magnitude for these. And for direction, someone's observed that direction perpendicular to A and B, and thus perpendicular to the plane of A and B, right? A and B, so two vectors that are neither orthogonal. Oh wait, I should say neither parallel nor same direction. So not parallel is what I meant to say here. Yeah, all I meant to say here was not parallel. Okay, talking about the direction, because there's no direction. If they're parallel, then the cross product is 0, the 0 vector. So there's no direction to that. It's just like a point, right? So when they're not parallel, the direction of the resulting vector is perpendicular to the plane formed by both the vectors, so therefore perpendicular to both individual vectors that you started with. Super important. You're going to have all kinds of problems where you've got vectors, and you need a vector that's orthogonal to the original 2, or the plane formed by the original 2. Immediately you should think cross products. That's what's going to do that for you. But what about this? What about the direction perpendicular to a plane? There's kind of an extra aspect to this. So if I have a plane, right, what direction is perpendicular to that? Yeah? This?
Yeah.
Is that the answer? Is that the direction perpendicular to this plane? Yeah, there's 2, right? There's this too. There's 2 different, so the opposite direction to that, to the first one I had. So the question is, which way does the cross product point? Does it point, if this was the plane of A and B, would it point this way or would it point this way? Okay, well, That we'll talk about in a second. So let's just summarize here. Maybe? Oh, nice. So the magnitude of the cross product is, how can we summarize what the magnitude of the cross product is? We summarize that. Okay, but that's how we calculate it. So, but more of a meaning type, yeah.
The product of the magnitudes, but only as much as they're orthogonal.
Right. So exactly, product of the magnitudes, just like dot product, right? The magnitude of the cross product is just like the dot product, and it's the product of the vector magnitudes, but only as much as now the vectors are orthogonal. Dot product was only as much as they were in the same direction. So cross product is only as much as they are orthogonal. Okay, the direction of the cross product. So that's our big takeaway here. The direction of the cross product is, we said, orthogonal to the original two vectors in the plane, but then we have a choice, right? Is it say this is the plane here? Is it this way or is it this way? So that we determine by what's called, so the direction of the cross product is orthogonal to both vectors, and thus the plane formed by those vectors. And then the way we know which one it is, there's two possibilities, is according to something called the right-hand rule, and we'll talk about that in a second. So the right-hand rule is what seals the deal, like tells you which one of the two orthogonal directions is actually the direction of the cross product. Okay. Any questions on that? Okay, so write your name on your sheet and pass it up. Upper right-hand corner, just write your name. While we're passing, any questions about that? So the last one on that sheet, where'd you get the pretty orange one?
I used to back.
Oh, I see your printout. I see. Okay, so let's do it. So the last one, what was the first vector? A was, as you're passing those up, tell me. First vector was? Very last one on the page.
0, -2, 0.
0, -2, 0. And?
4, 0.
Perfect. Okay. So we're going to kind of dissect this particular example and talk about direction and magnitude. Do you have them all? All right. So this is your chance to turn it in. It's not going to be. I'm not going to take it at the end of class. Okay. This is your chance. So let's draw those. So A is 0, -2, 0. We're going to draw them in standard position. Standard position means put the tail at the origin. So then in standard position, the tips of the vectors just have these same coordinates. We talked about that, right? So 0, -2, 0. Let's get a pretty color here. Be like this. That's my vector A. And then vector B is 4, 1, 2, 3, 4, 0, 1. So I'm going up from 4, 0, 0, 1 unit. So that's B. And so what do you notice about these two vectors? Anything special? So B is in what plane? What plane is B in? The XZ plane. The XZ plane. And A, how can you qualify where A is? Better than the YZ plane, it's what? Y-axis, right? So if A is in the Y-axis and B is in the YZ plane, XZ plane, excuse me, what can you say about these two vectors? Do you see they're perpendicular? They're orthogonal? Let me try to draw that. Let me try to draw it again. Should be heard. Okay, so that's a right angle right there, right? That's a right angle. So everyone, can you imagine that that's a right angle, right? So what do we know right away about the cross product here? What do we know about the cross product? What, the cross product is going to be the magnitudes product? The magnitude of the cross product is going to be magnitude of A times the magnitude of B, right? Because these are orthogonal, and that's what the magnitude of the cross product is. It's the product of the magnitudes so much as they are orthogonal, and they are orthogonal, so it's going to be the product of the magnitudes. So let's do it. So what's the magnitude of A? 2. Magnitude of B is? Square root of 17. So we're half done, all right? We know that whatever the cross product is of A and B, we've got its magnitude is going to be 2 radical 17. Okay, what about direction? So the direction, so this is kind of like on a plane that's, here's the horizontal plane, that's the XY plane is horizontal. So it's kind of on a plane that's tilted up like this, right? See that? So it's like coming up at, it's as it comes toward you, the plane is coming up, right? As it comes toward you. So can you imagine the two possible directions that are orthogonal to that? Can you imagine the directions that are orthogonal to that? Parallel to what? So the orthogonal to that plane is parallel to what, could you say for sure? Parallel to the z-axis? Parallel to the xy plane? Parallel to the xz plane? He said yes, it's parallel to the xz plane. Do you see that? Yeah, so if I put the tail here at the origin again, I'm going to get vectors in the xz plane that are orthogonal to this. Do you see that? But vectors are mobile, so I can't say it's in the xz plane. It's the vectors just, in general, it's parallel, right? So it's going to be something like this, or this way. Do you see that? And that red line is in the xz plane. It's in that plane that's perpendicular to the screen coming at you like that. So the question is, which way? All right, so here's where the right-hand rule comes in. So with the right-hand rule is you take your right hand, you point your fingers in the direction of the first vector, A, so I can do that. So here, I'm pointing my fingers in the direction of A, and now I rotate my finger, keeping them in the direction of A. So I'm going to rotate my hand so that when I curl my fingers, they curl towards B. So how do I have to rotate my hand? Pointing in the direction of the first vector, so that when, let's see, like this. So when I can curl towards B, it'd be like that. And then my thumb will show me the direction of the cross product by the right hand. So is it exhibit 1 or exhibit 2? 1, right? So I'm going to turn A until I can curl towards B, and then my thumb tells me the direction. That's called the right hand rule. So A cross B is this one back here. So I got the direction, the general direction of it, and we know the magnitude is 2 radical 17. So then what about B cross A? So with B cross A, again, I'm going to point my hand in the direction of B and rotate it until when I curl my fingers, they curl towards A. And so then my thumb tells me where B cross A is, which is opposite direction, right? So A cross B, or B cross A, has the opposite direction as B cross A. Did the right-hand rule make sense? Point your fingers in the direction of the first vector and then rotate until when you curl your fingers, it curls toward the other vector, and then your thumb tells you the direction of the cross product. So we're interested, if we're doing A cross B, we're interested in this one that's pointing up and back into this, back behind the screen. Okay, so that has some components, right? So how do we get the components of that vector? How do we get the actual vector? Okay, so we got its magnitude, but if it were an orthogonal, this would not, and then we're in R3, this would not be an easy task, right? If you got vectors that are just cattywampus in R3, how are you going to find the angle between them? That's a hard task, right? To do the sign. So this was easy because we had orthogonal vectors, but if not, in R3, not so easy. So it would really be nice just to have a way to get, given the vector A and B, what are the three components? So here's how you do that. Set up a matrix of the first row being I, J, and K. Second row being your first vector, so 0, -2, 0. Third vector being the third row being the second vector, 4, 0, 1. You set up a matrix like that. The cross product, you can find the components by doing the same algorithm that you do to find the determinant of that matrix. If you remember, if you've ever had matrices before, any way you want to find the determinant of that 3 by 3 will give you the components of the cross product. So I'm going to show you the way that I prefer. What I do is so what I'm going to do is I'm going to take the first two columns and rewrite them again here. This is one technique for finding the determinant of a 3 by 3. You rewrite the first two columns, and then there's 3 diagonals down to the right. Let's see if yellow shows up. Does that show up on the screen? Perfect. There's 3 diagonals down to the right now that have 3 factors. I'm going to multiply down each of those diagonals and then add them up. So I'm going to have -2i. So I'm multiplying down the diagonals. 0j and 0k. Am I good so far? Do you see that? And then I got 3 diagonals that go down to the left. 1, 2, 3. And I'm going to multiply down to the left on each of those 3 diagonals. And I'm going to subtract all those. So minus -8k, that's the first one, minus 0i, minus 0j. All right, did everyone follow what I did? So 3 diagonals down to the right, multiply and add. 3 diagonals down to the left, multiply and subtract those 3. And then simplify. So how many i's do I have? -2i, what's my j? 0j, is that right? K is 8. So does that vector, just by glancing at that vector, does it agree with what we decided the cross product should be? I got -2, 0, 8. Does that look like it could be correct, the orientation of it? Yeah, we said back and up, right? So -2 back and 8 up. I just didn't draw it long enough, right? All right, now look at this. What's the magnitude of -2, 0, 8? What should it be? It better be 2 radical 17 or we did something wrong, right? So magnitude is 4 plus 64, square root of 68, which is 4 times radical 7, or 4 times 17, which is, got it. So the direction, so doing this algorithm to get the actual components of that cross product vector, we agree with the direction by the right-hand rule, we agree with the magnitude by products of the magnitudes. Questions on finding the components of the cross product, direction, magnitude? We're good? Easy? I hope it's easy, because it's going to get a lot harder. Last chance, questions. Okay, so then we've got these two tools, dot product, cross product, and we see this kind of parallelism to them, right? So we've got applications that use both dot product, or some applications use dot product, some applications use cross product. So the question is, what do you use? What do you use in a given application? So when would you use dot product? You'd use the dot product when the quantity that you're computing is maximized when, right? So the product that you're trying to figure out, dot product would be used if that quantity that you're calculating, when would it be maximized? What's that? Yeah, so when the contributing vectors are in the same direction, right? So dot product is for quantities that are optimized or maximized when your contributing vectors, your original vectors, are in the same direction, and then 0 when orthogonal. And then cross product is going to be when's the cross product going to apply? For quantities that are optimized and maximized when the contributing vectors are orthogonal and 0 when parallel. This is how we know what to do. This is how we know what to use. If we look at a situation and, oh, we know that's maximum when the things are in the same direction, like work, right? Work is maximized when all your force is applied in the direction you end up moving. Dot product. Work is dot product. All right, so let's look at some new ones and try to figure out what they are. Dot product or cross product. Good. So torque. Torque is like turning force or twisting force. Okay. So this vector here. So what we've got here is we've got a moment. It's called the moment arm. It's the R vector. And the tip is at your point of rotation. Sorry, tail is the point of rotation, and tip is where you apply the force. Okay. And then this is our force vector. Now, the angle between vectors, we're talking about orthogonal parallel. The angle between vectors is always the angle when the vectors are tail to tail. So that's why I drew the force vector again over here. So we could figure out what the angle is. So I drew it here for the angle. But really, the force is applied here at the tip of R, right? That's where the force is applied. But I moved it here so we can see exactly what angle we're talking about, which is this right here. Okay, so that's our angle theta. So then I can come up here, and this would also be theta. So question, dot product or cross product? So how do we get maximum twisting force? How do we get maximum twisting force? By taking as much of F as orthogonal to R, or as much as F as in the direction of R? So I heard both. So I want to get I want to twist this thing as I want to, if I wanted to twist this thing, am I taking the orthogonal component of F to R to twist it, or am I taking the parallel component of F to R to twist it? Orthogonal, you should be thinking orthogonal all the way, right? If you take you're just gonna pull on the end of this wrench, and that bolt's going nowhere, right? Right? How are you gonna twist the wrench? How are you gonna twist the bolt? You're gonna push this way, right? So if the force is applied in the way I've shown it, it's only the part that's going, the part of that vector that's this way is gonna turn the bolt. orthogonal, right? So we want this part of F. So what is the magnitude of the torque then? What's the magnitude of the torque? Okay? So if we didn't know cross product, how could you write the magnitude of the torque? We got the vector F, the vector R, and angle theta. So how can we write the magnitude of the torque? It'd be magnitude of R
times
the portion of F, and what would that be? How would you get the portion of F orthogonal to R? What would you do?
magnitude of F sine theta.
Is that what you're going to say? Should make sense, right? I'm going to take this is the vector F sine theta, or has the magnitude F sine theta. That's what's going to contribute to twisting. That's an F. But what is that? What is the magnitude of R times the magnitude of F sine theta? Is it the cross product? It's not the cross product. It's the magnitude of the cross product, right? Cross product is a vector, right? Cross product is a vector. So it's so yes, it's kind of the cross product. It's the magnitude of the cross product. Which means that the torque itself, well, this was the magnitude of the torque. So the torque is defined as the cross product. So torque is a vector. It has direction. What's the direction of the torque? What's the direction of the torque? Is this the direction of the torque? That way? Nope. How do we get the direction of a cross product? Using right-hand rule. So which way is the direction of the torque? So like pointing out of the screen by the right-hand rule. You're gonna point your hand, your right hand, in the direction of R, and then turn it until you could curl your fingers towards F. The direction of the torque is out at you guys, orthogonal to R and F, out at you. And that's exactly how bolts are designed, because if you turn this wrench left, what does the bolt do? It comes out, right? Lefty loosey, righty tighty. Okay, so if you were to actually turn this wrench this way, the bolt would come out at you, right? So it's a perfect example of torque. So the direction, in this case, direction of tau is out of the screen. Exactly what the bolt would do if you twisted the wrench that way. So the direction of torque, so we're twisting in the plane of the screen, but the direction of the torque is actually orthogonal to that plane, the plane of rotation. Does that make sense? Okay, another example, another application. Any questions about torque? So torque has magnitude and it has direction. Magnitude is the magnitude of the cross product, or RF sine theta. Direction is orthogonal to the plane of rotation. Orthogonal to the plane of rotation. Okay, so here I'm showing vector theta increasing, two vectors of theta increasing. So for any given theta, do you see that there's a unique parallelogram that's created by those two vectors? Can you imagine that? Given if I paused it, do you see that there's a unique, only one parallelogram defined by those two vectors? Do you see that? Here's what that looks like. gold. All right, so now I'm interested in, I want the area of the parallelogram. The area of the parallelogram. Is that a matter of cross product or dot product? The area of the parallelogram. He wants dot product. She agrees. Everyone agree? Dot product? Dot product is for quantities that are maximized when what? Same direction. Here the vectors are in the same direction. So if we want to do area, we want dot product. Is that right? Okay, now some people are shaking their head. Right? Where's the area maximized? When is the area maximized of that gold parallelogram? More like this, right? Yeah, here's the maximum area. You thought I'd give you one of each, right? Okay, so dot product or cross product? Cross product again, right? Cross product again. So let's talk about the area. So I'll just give a generic case there. So here I've got, say, vector A and vector B. And I want the area of the parallelogram. The area of the parallelogram is, and this is theta. What's the area? Remember how to find the area of a parallelogram? Yeah. It'll be okay. So yeah. So let's see how that is. So if we didn't know anything about cross products, and I gave you this vector A and B, how could you write an expression? Yeah, you're right, and then we're going to get there. That's right. But if you didn't know anything about cross products, how would you write an expression that gave the area of parallelogram? Anyone know? Yeah, Andrew.
Base times height.
Base times height. Okay, what's the base? Good. What's the base?
Vector A.
Magnitude of vector A is the length of the base, and then what would the height be?
The height would be magnitude
Magnitude of
vector B.
B, sine theta. Lo and behold, what's that the same as? Magnitude of the cross product. So look, the area of the unique parallelogram formed by two vectors, that area is the magnitude of the cross product of those two vectors. We know that's 0 when they're parallel, right? Cross product is 0 when they're parallel. Maximized when orthogonal. What's the direction of A cross B here? What's the direction of A cross B? Toward you or into the screen? Towards you, right? So it would be A cross B towards you. B cross A would be B cross A would be into the screen. Okay? But the direction, if you're talking about area of a parallelogram, the direction doesn't come into play because we're just talking about a quantity, right? Not a scalar, not a vector. So that's why I use the magnitude of the cross product to get area. Later in the course, we'll talk about an area vector at the end, toward the end. An area vector, and that's truly the cross product. What its magnitude is the area, and its direction is orthogonal to the plane of the parallelogram in one way or the other. But for now, all you need to know is just to calculate the area. Okay, so while I take attendance, I got one last thing for you. So volume of one of these things. I think it's called a parallel pipette. It's fun to say. Parallel pipette. Volume. Doesn't matter a dot product or cross product. Okay. Brainstorming time. You either making progress or you're getting help. You guys work together. Think about this. Is it dot product or cross product to get the volume of this? So what is the volume of a prism, just in general? Let's just talk about that. Volume of a prism is? What's that? Area. So now it's area of the base times height. So there's kind of a hint to get started. Volume of a prism or a cylinder is area of the base times the height. Okay. See what you come up with. I'll take attendance. Anyone want to share your thoughts here? John?
I think it's B cross product A.
All right, let's just start right there. Why are you doing that? So you're going to do B cross A?
Yeah. Because that'll give you the.
What will that give you?
That'll give you a vector that's kind of like straight up.
B
Or A cross product B.
A cross B?
Sorry.
Okay, that's okay. So you said the direction will be straight up.
Right.
And why'd you choose cross product versus?
Because you want to find the vector that's perpendicular to those two.
Okay. Is a vector perpendicular to A and B? That's in the same direction as what? A cross B is in the same direction as C? Nope. It's in the same direction as what? The height of this thing, right? Where's that? Right there. Right? And that's going to be important because we know the height is going to be important. So A cross B, it kind of achieves two things, right? Its magnitude is? Area of the base, right? So its magnitude is area of the base. And its direction is in the direction of the height, which we're going to need, right? Okay, what about from there?
And then you're going to want to dot product that with C to find like how much C is in that direction of the height.
So he's saying how much of C is in the same direction as H. Agree? Because the amount that C is in this direction of H will be the magnitude of H. So A cross B, then what? Dot C. So this will be, what do we, the product of these magnitudes, right? The product of the magnitude, that's the base, area of the base. And then, but then only as much as C as is in the direction of H. That's exactly what we need. Did anybody else get that before we started talking? Anyone else have that? Yeah? Good. Does it make sense? So this is the area of the base, its magnitude. And then when we dot it with C, we get the product of these magnitudes, but only as much of C as is in the direction of A cross B, which is the height. And that's exactly what we need, area of the base times the height. So it's both. It's both cross product and dot product. So this is the product of A cross B and C, but only as much as in the direction of H. So we get the product of the magnitudes, and then the part of C in the direction of H gives us exactly what we need, area base times height.